Hello, everyone. Scott McDonald. I'm an application engineer at the Siemens Corporation for the Simcenter testing products. Frequency-based substructuring, this is what we're going to talk about today. First, we're going to very briefly talk about what it is, kind of why people use it or why it's a thing we're talking about today. But ultimately, we're going to focus on how it can help us get this thing called a system FRF. This is the whole end goal of what we're talking about today, is a system FRF for an assembly of multiple different components. What is frequency-based substructuring? This is not something that's necessarily new. It's been used particularly in the CAE or simulation parts of the world for a while. And it came about because if you think about a finite element model, in this case, I just have three different boxes, each representing a different component, so different structures. And each of these models has hundreds of thousands, if a million nodes or something, and a very discretely defined mass, stiffness, and damping matrices for all of those elements in those models. This is great for predictive work with any one of these models. The problem comes in if we were to try to assemble these models, put, let's say, a subframe into a car body and see how those two models interact together. It becomes prohibitively computationally intensive. The strategy we're going to apply, there are a couple here, one of which is making an FRF model of those structures, generating a family of FRFs that describes how the energy flows between all of its inputs and outputs. And we can represent that very complex or high resolution finite element model with a simpler FRF model. And these FRF models can be combined together. We just have to do it in a smart way. And that's where frequency-based substructuring comes in. Essentially, we're going to collect FRFs, simulate or test FRFs between all of the coupling points, the inputs and the outputs of the structure, whatever those might be. And we're always measuring or simulating in free conditions. So we never want to have them constrained or bolted down or anything like that. If we have mounts in between our components, up here, I'm showing component A is this electric motor. Component B is maybe the vehicle body that we're going to put it in. And there might be some elastomeric mount that goes between those two. So we have FRFs for component A, FRFs for component B, and then possibly some dynamic stiffnesses for the mount that goes between those. The FBS's job is to create a FRF or a family of FRFs of the assembled system. Feed it FRFs for component A, we feed it FRFs for component B, dynamic stiffness for any mounts that we have, and it outputs for us the FRFs for that assembled system. So that's why we're using it. So how is this used in industry? Why are people talking about it? If you think of an example from the automotive industry, so if there's a supplier and they make steering racks, for instance, they have their physical prototype of their steering system, and the OEM or the car company has their vehicle structure that they're going to be putting that steering system into. They've also got a physical prototype. The traditional way of doing that is, okay, drive the steering rack over to the OEM, install those two, turn everything on, and then see how they behave together. The problem is if you have a noise or vibration problem at this stage, you're going to be slow to react, and it's going to be expensive and hard to change either or both of those systems to solve this problem. This is the old-fashioned model where you waited and you built all these prototypes and you just tested every variant. And if there was a problem, you fixed it by whatever means you had to fix it. But it was slow and it was expensive. And that's why we would like to not have to rely on that method anymore. So alternatively, the supplier can make what we call an invariant source component model of their steering rack. And that invariant source component model consists of block forces, which are the loads that this steering rack are going to generate, and then some FRFs. We're going to call them impedance FRFs, and we'll learn more about what that means. But they essentially work on their component and they generate these two pieces of data. The OEM, for their part, gets their own impedance FRFs and target FRFs for their vehicle body, either through simulation or test, and then any dynamic stiffnesses of the mounts that they're going to be using. We can then, with FBS, or frequency-based substructuring, virtually assemble that steering rack into that body with that elastomeric mount and predict with good accuracy how the noise and vibration performance is going to do with that system. If there's an issue, these are either just prototypes or there could even be simulation models. They're virtually being assembled. And so if there's an issue, we can much more quickly react to that, and we can do it earlier and earlier in the vehicle development process and solve these problems easier and more quickly up front, which is good news for everybody. Okay, so that's why we're using it. It's going to enable us to virtually assemble these components. So I've got the output of an FBS here, and I'll break down these parts. It looks pretty complicated, but it's really just made up of some, I think, easily understood parts. And this is the roadmap of where we're going to end up. The end result is we want to be able to predict the system performance with this virtually assembled system. In this case, let's say it's that electric motor into the vehicle body that we were showing before. Ultimately, we want to be able to predict the driver's ear microphone response to that electric motor. Okay, so the pressure at 0.5, which is just our final operator ear position for this combined system A, B. Okay, we're going to take some components or some pieces. So for source A, it's this electric motor, and that's the source A. And so you'll see this superscript A for anything that comes from system A. And you see these H's and this F. F is just a block force. We're not going to talk too much about this, but this is the forces that the electric motor put out. And then these H22 is a matrix of FRFs, and we'll talk a little bit more about that. But it's just FRFs on the motor itself at the connection points. There's also H superscript B, which means it's for the receiver B, and we see H33, which just means it's FRFs at 0.3 to 0.3 from 0.3, and then also a cross FRF response at 0.5, the driver's ear, due to an input at 0.3. And then if we have an elastomeric mount, here is our dynamic stiffness. So this is the end result. What does it get us? Well, this conversion matrix are these middle terms, and that is what allows us to convert these forces and these responses in a couple different ways, depending on which is more useful to us. This top line you see is the assembly contact forces. And if you've ever done a traditional TPA or transfer path analysis, these contact forces or interface forces is what we are after, and we apply those assembly contact forces at the start of our path. So we would take those contact forces, put them in right here, and then see how the response is broken down into the different paths. So this is shown as a single connection point here, 0.3 and 0.2. Realistically, this could be 2, 3, 4 different connection points between the motor and body. We're just showing it as a single point. And so in traditional TPA, we take these assembly contact forces and see how they sum up to be our driver's ear, and then understand who's most responsible for that power transfer. The way we're going to use it today is to generate this assembly target transfer function. So we want to come up with these HAB essentially. So the FRF matrix for the assembled system A and B together. The cool thing about this is once we get this assembly transfer function, we can then apply blocked forces to that. And as these blocked forces are just a property of source A, we can use it and swap out that motor for a different one. We could change the calibration of that motor and input some new block forces and get an entirely new prediction very flexibly, because this is just the transfer function for our assembled system. So that's where we're going to go. We're going to get into the meat and potatoes of how we got that equation that we just broke down. Okay, so how can we get a system FRF? For our discussion today, we're going to look at a pretty simple system, system A and system B. In this case, we're going to use two passive components. Before we were talking about an active component with the electric motor where forces were generated inside that and then passed into the receiving structure. We're just going to look at a subsystem between the subframe here, so where the motor might get mounted onto, but then this subframe gets mounted into this vehicle body. And we see our connection points, 4 connection points on the subframe. It gets bolted up right up here. And if we've got both of these physical test articles, I can just take a bunch of FRF measurements on system A. I can take a bunch of measurements on system B, and I can then even put system A right into system B, right? I can assemble them and just take the measurements once. I don't even need to bother with the individual component FRFs because I have all the parts. I can just put them together and measure my system FRFs in one shot. However, this isn't always the case, right? We want to be able to do this investigation earlier. And so in this case, there is no vehicle body yet. It's just a simulation model, and we still want to be able to do this. So we can't bolt a real subframe into a computer model. So we need to do this frequency-based substructuring to simulate or replicate that system impact test where we get those system FRFs. I've represented these two systems with just these simple blocks, system A and system B. Again, I'm showing one connection between these two systems. These could be multiple different connection points. The principles all hold the same. It just gets obviously more complex in terms of the amount of FRFs and harder to follow in a presentation standpoint. So we're just going to represent all of those connections with a single connection. What we're after, again, is this system AB FRF. So it's a family of FRFs that describe how inputs on the system A end would result in responses on the output side of system B, but as an assembled system. Each system has input and output locations, and these are color-coded, and purple and the letter I here just means it's an input location. Forces come into system A at this location. The C denotation in blue are the coupling or connection points here. And the subscripts here just mean it's the connection or the coupling point on system B. This is system A, input on system A. And then finally, the output is in orange, and that's the output on system B. So we expect forces or loads to be going from left to right in this system, just because this is our subframe in this example, and this is our body receiver. And output on system B is really our driver's ear microphone. Some nomenclature. I'm going to use the letter H to represent an FRF or a family of FRFs. Again, this superscript just means it's an FRF on system A. And then these subscripts will tell us where this FRF is taken from. Remember, an FRF is just output over input. And so CA over CA means the output was at coupling location on system A. The input was also at the coupling location on system A. So we would call this a driving point FRF or local impedance FRF for system A at that coupling location. System B, there are also cross-term FRFs that we're going to be looking at where we have an H or a FRF on system B, and the output is on the output of system B, and the force input was at the coupling location on system B. HB, OB, sub-OB / CB just means it's hit here, measure here, and it's this cross-term FRF. Again, every time you see an H, just think frequency domain function called an FRF. The end result is what we want. This is the end result here is a system FRF H for combined system AB, where the response is at the output of B and the input is at the input of system A. So this is the end of the road if we are successful. So as we've been talking about, FRF is really just measured as the response over the measured input. And so in an impact testing scenario, you're measuring an acceleration at some location and you have a calibrated force hammer and you're impacting your structure and measuring those two values. And then we just take the ratio of those, and that's our FRF. To use these FRFs and our forces in order to predict a response, we can always multiply our operational force times an FRF and calculate what the response is going to be. So we have some operational force. We're just showing it as a constant broadband force here, but we multiply that by the FRF at some location, and we can predict what the response at that location will be. That's what the FRF is helping us do. So we're going to be using this relationship as we go forward. In order to get us there, I'm going to split our system into two pieces, System A and System B, and look at them separately, because remember, we're going to acquire our FRFs separately and then combine them using FBS to get the system FRF. So for System A, we have, again, inputs, coupling locations, responses, and forces. And if we look at all the possible locations, we could have force operating on System A, we could have input at the input, we could also have a force acting at the coupling location. And for our purposes today, we're only going to be talking about the response at the coupling location. There is, of course, theoretically a response at the input side of System A, but we're not really interested in that today, so we're going to leave it out. So we have one function or one value that we're trying to compute here, and that's the response at the coupling location of System A. That's going to be the force at the input multiplied by this cross term FRF, so the response at CA from IA. We're going to add to that the effect of the force at CA to CA. So this cross FRF multiplied by this force multiplied by the local impedance FRF. Those two summed together will give us the response at the coupling location on System A. We're going to do the same thing for System B. Here we are going to, again, have two forces. Here we are going to have two responses. So the response at the coupling location and the response at the output location. Okay, so we have two equations we're going to be building up here, much in the same way. So for CB, so F times CB local plus this force times the cross FRF this direction gives us this response at the coupling location. Then we take this FCB times the cross term plus the F at OB times its local FRF. So that's the response at the coupling and the output for System B. Now, we're going to start working with this as a complete system. I'm going to make some assumptions here, again, for clarity. The principles I'm going to show are going to be for a rigid connection. Okay, so I'm bolting this subframe directly into my body. There's no elastomeric mount. From my past, the ride and handling guys would have loved this because it gives them ultimate control, right? As a noise person, I did not like this because it made it a lot louder. But for our discussion today, we're going to have it be a rigid connection. With that assumption come a couple different conditions. With that rigid connection condition, we say the response at the coupling location on A, that has to be equal to the response at the coupling location of B. They're bolted together, so they are equivalent. So all I'm going to do is I'm going to flash back to this slide and to this slide, and then put them together, and we come up with this equation down here. Okay, so I've just taken these two terms from their individual system pages and brought them down and made them equal. So that's the first condition from our rigid connection. There's also another one, which is the forces have to be equal and opposite, right? The sum of the forces at that coupling location need to add to 0. So that means F sub CA, the force at the coupling location on System A, is equal to the negative version of the force at the coupling location from System B. I'm going to take this equality here in the center, and I'm just going to sub it in to this guy down here and say FCA is negative FCB. And so I just sub him in there. So now I see a couple FCB terms. I'm going to do some further work here, but I'm going to add one more boundary condition in here to help us simplify this a little bit more. And the boundary condition for our example here is that there is no force coming in to the output on System B. We said this orange response point on the output is a driver's ear microphone. And this cross FRF is like a P over F for our car body, if you want to think of it that way. I hit with a hammer here and measure a pressure response here. When I'm doing that, I better not have any sound being generated external to the system and acting coming this direction to the output. That means an unmeasured source, and it's bad news. So I'm going to set the force coming into the output of system B to 0. Okay, so that means I can just take this term right out of this equation down here. That guy gets lopped off. We have just a simple 3 terms here. I'm going to move this CB over here. All I did was just add this to both sides. So I'll group my 2 CB terms on the input. So system A is over here on the other side of the equal sign. And now I'm just going to factor this F sub CB out. And so F sub B times these 2 H matrices are equal to the force at the input of system A times its local impedance, FRF. I've just shrunk the font size there because I want to do some more work over here. So nothing has changed in this step here. I'm just going to rearrange this a little bit, and I'm going to take this term right here, and I'm going to move it over here to isolate F sub CB, which is what I show right in here. And I've put a red box around this because this is a pretty significant waypoint on our journey. I'm relating a force at the input to system A to the force that will be experienced at the coupling location on the second system, system B. And we see it's this relationship between these local and cross FRFs between system A and system B. So this is a good achievement, but we're not quite all the way there. I'm going to add in one additional thing that I can help make this a little bit more useful. And I see I've got F sub CB defined here. Well, if I look back at my system B equations, I've got some FCB terms here. And realistically, I'm only really interested in the output response, right? I don't really care about the response at the coupling location. It's like it's inside my system. I'm pushing on the input of A, I'm measuring on the output of B. I don't really care what happens on the inside term, so I'm going to ignore him. And so now I'm going to isolate F sub CB from this equation that I have from just the system B analysis. Our F acting on the output of B is still 0. And so this term goes away. And so I can isolate F sub CB as just X sub OB divided by the cross FRF output from the input across system B. So now I've got FCB identified in 2 different ways. I'm going to take this and I'm going to shove him into here for this F sub CB term using this new form of it. This is with that insertion or substitution done. And now I'm really close, right? This is what I'm after. This is what I'm putting in. So the only thing left to do here is take this H cross FRF term from system B and multiply it over here. This is the full system FRF for system AB. It relates the forces on the input of system A to the output on system B. So this is our system FRF. We have virtually assembled these 2 systems just by supplying some FRFs on the 2 individual systems. This is a simplified case, but the process is the same if I were to include mounts or not a rigid connection, things like that. The process is very similar. This helped me understand and visualize what was going on. So I wanted to share that with you today. So what does this mean? Well, it means I took system A and I shoved it inside system B, and I came up with this equation. Now, if I have some measured force acting out of my electric motor, acting on the coupling points on system A, I can use this system AB FRF to predict what the driver's ear microphone will be as the output of system B. Because I have a combined system FRF, I can do that kind of prediction. Even if one of these components or systems is a simulation model, maybe they're both physical specimens, but one's in Europe and one's in the United States. And we don't want to take the time or money to ship them to the same location to be tested. This same principle could be used for that scenario. So it's a very powerful tool. There's a lot of cool applications for it. Transfer path analysis and component-based TPA being one of the most popular. That is a crash course through frequency-based substructuring.